Yes, friends, today's lecture number 10, we shall discuss about charge distribution and electric dipole. Let us start. देखिए, basically there are three types of charge distribution. One is volume, then surface, then line charge density. So just basic idea about this. In practice, we deal with charges much greater in magnitude than the charge on an electron, as you can see in this diagram. So we can ignore the quantum nature of charges and imagine that the charges is spread in a region in a continuous manner. Next point is such a charge distribution is known as continuous charge distribution. Okay, the formula is this: F vector is equal to Q naught upon 4 pi epsilon naught integral dq upon r square in the direction r cap, as you can see in this diagram. Okay, now continuous charge distribution in case of volume charge density. How to define this? As you can see in this diagram, F vector is equal to Q naught upon 4 pi epsilon naught integral dq upon r square in the direction r cap, as seen from this diagram. There is a small differential volume. Okay, then volumetric charge density, suppose rho. In that case, rho is equal to d dv of q, that is dq is equal to rho dv. Now, further, if you put the value of dq in equation 1, you are getting F vector is equal to Q naught upon 4 pi epsilon naught integral rho dv upon r square in the direction r cap. Okay. Next is, in case of surface charge density, what is continuous charge distribution? How to write the expression? Similarly, we can say that F vector is equal to Q naught upon 4 pi epsilon naught integral dq upon r square r cap direction. This is equation 1. Now, surface charge density, suppose sigma. Then we can say that sigma is equal to nothing but dq upon ds, that is dq upon is equal to sigma ds. So put the value of dq in equation 1, you are getting F vector is equal to Q naught upon 4 pi epsilon naught integral sigma ds, this is important, upon r square in the direction r cap. Okay, now next is linear charge density, how the charge is distributed in this case. In this case, suppose as per the diagram, this is a linear charge distribution along a length of wire. Okay, then F bar or F vector is equal to Q naught upon 4 epsilon naught integral dq upon r square in the direction r cap. Linear charge density, suppose lambda. Okay, then lambda is equal to dq upon dl, or you can say dq is equal to lambda dl. So finally you are getting the F vector is equal to Q naught upon 4 pi epsilon naught integral lambda dl upon r square in the direction r cap. So these are three different types of charge densities and according charge distribution. Now next topic is electric dipole. A pair of equal and opposite charges separated by a small distance is called an electric dipole. This is the diagram which depicts the electric dipole configuration. There are two charges of equal and opposite magnitude at a distance of 2a. Then dipole moment is just opposite to the electric field, which is P vector. Okay. Now further discuss this dipole moment. So as I just told you about this diagram, so number one, this dipole moment is nothing but a vector quantity. Vectorially, you can say vector P is equal to Q into 2a bar. Okay. Now magnitude is P, which is Q into 2a. Next is the direction is nothing but the negative charge to positive charge, means just opposite to that of electric field. Example of electric dipoles. Examples of electric dipole means the dipoles are common in nature in molecules like HCl, H2O, C2H5OH, etc. You can observe this dipole, electric dipoles. The center of positive charges does not fall exactly over the center of negative charges. Such molecules are electric dipoles. They have a permanent dipole moment. For example, in this case, HCl. So this forms a dipole. Now, ideal or point dipole. We can think of a dipole in which a size 2a, means the distance between the two charges tends to 0 and the charge tends to infinity. So in such a way that the dipole moment P is equal to Q into 2a has a finite value. Such a dipole of negligibly small size is called an ideal or point dipole. Dipoles associated with individual atoms or molecules may be treated as ideal dipoles. You can see in this diagram, this two charges of equal and opposite magnitude have a distance of 2a. Then if 2a tends to 0 and q tends to infinity, then P is equal to Q into 2a, which is nothing but a finite value. Now, what is dipole field? The electric field produced by an electric dipole is called dipole field. You can see in this diagram, there are two charges of opposite nature but equal magnitude at a distance of 2a, then dipole moment as shown in the diagram. Now, what is variation of dipole field with distance? See, the total charge of an electric dipole is 0, but the electric field of an electric dipole is not 0. Dipole electric field at larger distance falls off as 1 upon rq, as we shall see just soon. In the derivation, we shall see that this dipole electric field is basically inversely proportional to rq. So electric field due to point charge falls off as 1 upon r square. We have already seen this thing. Okay, this is the difference. Now electric field at an axial point of a dipole. How to discuss this or how to analyze? For example, in this case, there are two charges, means this is a dipole setup. Just discuss now. Now there is a point P which is at a line joining to, if you are extending this line, axial line, then at point P, how to calculate the field? So field would be there due to the two charges. One is due to plus q, another is due to minus q. So accordingly, there will be two fields. Okay. So E axial is nothing but 1 upon 4 pi epsilon naught 2p upon r cube if A is very small as compared to R. Okay, means the distance is very large as compared to the dipole, this 2a distance. Okay, now in vectorial form, E vector is nothing but 1 upon 4 pi epsilon naught 2p upon r cube in the direction of p cap. Okay, where this is nothing but the dipole moment. So if a is very very small as compared to r, now let us see the derivation, how to derive this. Again, consider this diagram. Okay, in this diagram, what is E due to positive charge? That is 1 upon 4 pi epsilon naught q upon r minus a square, because the distance of positive charge with respect to this point is nothing but r minus a, as you can see in this diagram, which is towards right. And similarly, E due to minus q is 1 upon 4 pi epsilon naught q upon r plus a whole square, because the distance of this minus q with respect to this point is r plus a, that is towards left. So these are two important equations. Now E resultant, which is axial, is nothing but the summation of the two. Okay, so if we are adding the two in this particular case, then you are saying that E axial comes out to be this q upon 4 pi epsilon naught r plus a whole square minus r minus a whole square, r is minus a whole square into r plus a whole square. If you further solve, finally what shall we get? That is 2pr upon 4 pi epsilon naught r square minus a square ka whole square. Now see another corollary in this case. For example, E axial comes out to be this 2pr upon 4 pi epsilon naught r square minus a square ka whole square. Okay, now vectorially you can say E axial is equal to 2pr upon 4 pi epsilon naught, that is into r square minus a square ka whole square, that is p1. So that's we have just discussed. Okay, this is how we derive this expression. Now for short dipoles, means in this which case the r is very large as compared to the distance between the two dipoles. In that case, E axial is equal to 1 upon 4 pi epsilon naught 2p upon r cube in the direction of p cube. तो जैसा मैंने आपको बताया था, E axial is basically inversely proportional to r cube. Okay, so note electric field at axial point is in the direction of the dipole moment, mind you. Okay, so this is all about today's lecture. No, okay, so we shall see you in the next lecture. Till then, Jai Shri Ram.